Hi, I'm Andrea, and welcome to the webinar. Thanks so much for joining us. We are very lucky to have Mike Pilone, the creator of HazelcastMQ, presenting today. He's going to explain why he wrote the framework, going into a little detail about its overall architecture, and give us a few live demos. Mike specializes in Java backend technology solutions. He is a software architect at the National Public Radio, which many of us know as NPR, and he's leading the Content Depot project, which manages their live audio stream management and automation. He also worked at Vangent, specifically on the NASA ECHO project and the Naval Research Laboratory with the Department of Defense. Before we get started, I want to ask you to feel free to ask any questions using the question box on the controlled panel. Mike will address these after he's gone through his presentation. And I'll turn it over to Mike now.
All right, hi everyone. Welcome to the webinar. Hopefully you can all see my slides now. So today I want to run through a little bit about HazelcastMQ, give you some background on myself and the project. Even if you're not directly interested in messaging over Hazelcast, hopefully this gives you some ideas of different ways to use Hazelcast besides just the shared cache concepts. So what I want to cover today is, like I said, an overview of HazelcastMQ. I want to talk a little bit about why I chose Hazelcast for the solution. Go into the architecture and some of the components within HazelcastMQ, and then look at some of the benefits and the limitations of where the library is right now. Look at some use cases where it'll probably fit in pretty well, a few where you probably want to avoid it, and then talk about some of the future work that I have in my mind, and things we can do with the concept going forward. And then I'll try to leave some time at the end for questions. Like Andrea said, my name is Mike Pilone, software architect with National Public Radio. I build, content management systems, the back-end distribution system that's doing the automation of the live streams, as well as all the file-based distribution out to all the stations. I don't have any affiliation with Hazelcast, other than using and really enjoying their products, but I don't work directly for them. All right, so let's get into a little bit about HazelcastMQ. So it really just started out as an experiment that I was personally interested in to see if you could do messaging over top of Hazelcast. It's really from there grown into a rather functional library that we're now using on a couple of solutions in-house and hoping to expand into a few other products pretty soon. So the goal was to layer more of a messaging focused concepts on top of the existing Hazelcast queue and topics. So, for example, introducing things like message expiration, request reply messaging, destination syntax, transactional queues and topics, etc. So, really just making it focused on making it easy to send and receive messages, and abstracting away a little bit of the lower level data structures that Hazelcast exposes. It's built on top of Hazelcast. It's a relatively thin layer, so that means it's really easy to cluster and scale out, just as Hazelcast itself is. And the goal is to keep it pretty simple to use. If you have any experience with JMS and Hazelcast, you can probably get a clustered message queue up and running in 10 lines of code and no more than 10 or 15 minutes. So the obvious question is, why another message broker? There's so many already out there. And so my personal experience is that most of them have grown really heavyweight, and they try to offer thousands of features to please everyone. But what that means is that they become a huge pain to configure and maintain. On a recent project, I spent weeks trying to get ActiveMQ to reliably deliver messages when you start integrating them with things like Spring and Camel. You just end up with so many little odd cases and configuration tweaks, and they expose so many knobs that you can turn. It's pretty easy to shoot yourself in the foot. You get things like connection caching, prefetching, persistence, flow control. And the problem is you don't see a lot of these problems until you go into production, and suddenly your message load spikes, and you realize that you're not delivering messages, or they're getting buffered someplace, or they're ending up in a dead letter queue or something. And then the next problem you run into is that as soon as you try to cluster or do failover with many of these solutions, things just start to fall apart pretty quickly. It really just seems, as an outsider view, it really seems like a lot of these products were not designed for clustering from the beginning, and so it ended up being just kind of an add-on that was done later. So some of the solutions use, advisory messages. Some use a shared file system, a shared database. Some only support master-slave, which means, you have failover, but you don't have any kind of scalability or clustering. And so these solutions just become problematic. As soon as you want to go to a 2 or 3 node cluster, you end up with a whole new set of problems, or just a ton of overhead with things like advisory messages getting passed around. So then there's some interesting other solutions like ZeroMQ, which kind of takes a different approach from the centralized broker. But as you start to read through the documentation, you really realize that it's slightly higher level than sockets, but it's still pretty low level. So as soon as you want to start doing cluster distributed message passing, you end up building a lot of stuff yourself. Amazon SQS, the simple queuing service, I think is a pretty good balance of simplicity and features. But if you're not running an EC2, you end up with a lot of network overhead because you're basically shuffling all your messages out to the cloud and back again. So ideally, you want something simple like SQS, but you want to be able to do it in-house, but still be able to scale. So that's kind of led me down the route of maybe I could do this on Hazelcast and use the scalability and the clustering that's already built in. So, given that, why did I pick Hazelcast? Well, the first reason was that I was already using it in a number of solutions, mostly for distributed locking and leader election type use cases. And I just found that it was way easier to configure and maintain than Zookeeper. If you want a 2 or 3 node cluster and then you want to use Zookeeper, you almost double the size of your cluster just to maintain the Zookeeper nodes. Whereas Hazelcast, you can embed it in process, or you can have one in process and a couple out of process. So it gives you a lot of flexibility there. So that was great for being able to stand up a cluster of machines pretty quickly. The other reason I really liked Hazelcast was that clustering is a primary feature. It's designed to be a data grid, and so unlike some of the existing brokers that we were just looking at, Hazelcast really takes clustering seriously, and it makes it incredibly easy. So it's not one of those things where it's great standalone, and then as soon as you cluster it, things start falling apart. So I knew right away that it was going to work for avoiding kind of a hub and spoke model and really being able to do a clustered solution. It's small and lightweight. I think it's a single jar. I think it's under 10 megs, which is fantastic. Means you can drop it in and not have to pull in everything else. If you look at things like ActiveMQ and Camel, they start to kind of slowly pull in more and more dependencies that you have to deal with. Hazelcast also already has queues and topics and transactions, so it makes my job a little bit easier. I don't need to build those data structures or map it to anything else. I can use the existing concepts. And then, of course, it's free, so that's it's always good when you can get something for free. But if you need the paid support and you need to go up to the next level, it's there and it's available. So that's I think a great model for software is for the small cases, you get it for free. You can try it out. You can build your solution. If you like it, then you can pay for support. All right, so let's jump into the architecture of HazelcastMQ. So first of all, it's split into multiple components. So you have the core component, and then there's layered on top of that, there's Stomp, JMS, and Camel, and we'll go through one by one and kind of explain what each one does. And then the goal is that with this architecture, I can continue to add more components and integrations as needed. In fact, right now I'm starting to look at a HazelcastMQ Spring to tie in some of Spring's transaction management with both Hazelcast and HazelcastMQ. So let's look at the core component first. That's the lowest level part of HazelcastMQ, and it exposes a kind of a JMS 2-ish API, I'm calling it. I didn't want to reinvent the wheel and have to come up with a new messaging system and a new API. A lot of people have already put a lot of thought into what makes a decent messaging API. They learned a lot of lessons from JMS 1. So if you're not familiar with it, I recommend checking it out. The JMS 2 API really simplifies things down a lot. And so Core uses that API to provide basic messaging concepts. For example, it introduces the message type, comment headers, producers, consumers, etc. So it gives you the concepts you expect from any messaging system. And then the consumers expose either polling or event-driven APIs, again, just like JMS2 or even JMS1. So, you can do your own polling using receive methods, or you can just register for, event-driven stuff. So if you have, reactor pattern, or you want to build a reactor pattern, you can build that in as well. And then using the underlying queues and topics within Hazelcast, you can get, pub sub, broadcast type functionality, or you can do point-to-point, over queues. All right, so let's take a look at some actual code, and you can see what this looks like. So I'm going to jump to a live demo here, which is always risky in a presentation, but hopefully everything will go well. So what I have here, hopefully you can all see the IDE now. So I just have a little simple application that runs the start method and then waits for you to do something, or runs the stop method. So in the start method, I'm just going to build a simple client that listens on a topic and then sends a message to that topic. So we're starting off with a Hazelcast instance, and I'm just going to create a simple config here that turns off multicasting just because I don't need it in this demo, so it'll speed up the start time a bit. This is nothing special. This is kind of your standard Hazelcast setup. So if you use Hazelcast before, it should look familiar. So we'll just create a Hazelcast instance equals Hazelcast. Okay. Then from there we can create our HazelcastMQ instance, and like I said, it's just a layer on top of Hazelcast. So I tried to build the API similar as far as construction goes. So you create a HazelcastMQ config. So we'll call this our MQ config, and then we'll set our Hazelcast instance on that. If you don't set one, it'll construct one for you by default. But if you wanted to configure it yourself, for joining a cluster or networking options, you can do all that and then just pass in which instance to use. This also allows you to share the Hazelcast instance across your application. So, for example, if you were already using Hazelcast as a distributed cache, you could use that same node. You don't have to use a separate node just for messaging. All right, and then we'll create our actual HazelcastMQ instance. MQ instance equals Hazelcast MQ new instance. So you can see the APIs are very similar for constructing your MQ instance, just like your Hazelcast instance. All right, so now we have them. So the root of HazelcastMQ, as far as how to get access to consumers and producers, is through a message queue context. Again, this follows the JMS2 API, if you're familiar with that. So what we can do is say that our MQ context equals MQ instance dot create context, and you can create a non-transactional or a transactional context depending on what you need. And this is what I'm looking at right now, linking into or integrating in with Spring's transaction support as well. So at that point, we have our MQ context, so we can create our consumers and producers. So let's go ahead and create a new consumer. And we'll consume on a destination. And so this is where you start to getting to some of the mapping to more messaging concepts, is that you use destination names rather than explicitly saying queues or topics. So for example, I can say topic presentation.demo. And HazelcastMQ will map that to an underlying topic within Hazelcast. And we'll assign that to our consumer. All right. So at this point, if I wanted to, I could use the polling operations to poll from the consumer. But instead, what I'm going to do is set a message listener so that it's event-driven, so that I don't need a separate thread to do any polling. So we can create a new HazelcastMQ message listener. And then we're just going to just print it out for right now. So we'll say %s got message %s. Okay, and then we'll just use the application name here just so we can see what's happening. And then you can see that what you receive on message is a HazelcastMQ message. So again, this is applying the message concepts where it gives you a standard structure for what a message looks like as it's flowing through Hazelcast. So it gives you a foundation to build on. And it has a nice convenience method for get body as string, so that'll get the body of the message out, and then we'll print it out. So at this point, we essentially created a subscription to this topic, and any messages that come in on the topic, we're just going to print out to standard out. So now we want to go ahead and send a message to that topic so we can see it work. And so what we'll do is we'll create a producer. And again, you use the context to create your producer on a destination. And then with the producer, you can send messages. And there's a couple overloaded sends where you can send, a fully built message. You can send the body, and internally we'll construct the message. And then there's some options as far as time to live, and a bunch of standard headers you can set on a message if you need to set any headers. We're just going to keep it simple, and we'll just say hello, hello world from the, and then we'll put the application name again. All right, so that should do it. So now we have a consumer that's listening on the topic, printing out the messages, and a producer that's going to send to the topic. So if we run this, we should see our own message show up because we're listening to the topic and we're now broadcasting on that topic. So if all goes well. Oh, did I forget to set the configuration? That's okay. Okay, so this was all the multicast stuff that I meant to turn off, but I think I forgot to set the configuration. But here you go, you can see that the application starts up and is running, and then we got a message, hello world from the core app. So again, this is where I should have set the config. So again, what happened is we subscribed and we're listening on the topic, and then we sent a message to that topic using the send method. So you can see it gives you, pretty simple producer-consumer model on top of Hazelcast, and it hides any of the dealing with the queue and topic. So this is essentially what the Hazelcast core gets you. And there's a bunch of stuff, like I said, as far as standard headers and message expiration and that kind of stuff. We don't have time to get into all that now, but it is all built into the core. All right, so let's switch back to the slides, and we'll continue on. Okay, so that was the core that we just looked at. So next, there's a component that builds on top of core called the stomp component. And so that's built on top of a library called Yeti, which right now is also bundled with Hazelcast, but I may split it out into a separate standalone library. And Yeti uses the Netty I/O framework for all the network I/O, and it implements the Stomp 1.1 and 1.2 protocols. And it does this by introducing a stomplet concept. And so HazelcastMQ Stomp implements a stomplet that basically binds stomp, send, and message frames to consumers and producers within Hazelcast MQ core. And so what that lets you do is expose a stomp server that maps all the messages to Hazelcast MQ core, which allows you to then basically start integrating components that are written in a bunch of different languages. So if you have components that are not implemented in Java, but you still want to participate in the message passing, you could do that through the stomp interface. This is a common use case that we have here because we have a number of C components that actually control a lot of real-time switching for live streams that are I would say soft real-time, sub 1 second real-time. And so we use those to control hardware, and then they can broadcast status information, or we can send command and control messages to them via the stomp interface. On the Java side, we can write everything using HazelcastMQ so that we don't need to directly address the components. So rather than go through a whole code demo, I'll show some code, but I'm not going to type it all up here. So we still have our core application running here. So I'm going to leave that running, and then what we'll do is we'll look at the stomp application. And what you'll see is it's very similar to what we just did in the core application. So first we're going to create, in this case I'm using a Hazelcast client, so I'm not running a separate data node. I'm going to become a client to the node that we started up in the core application. So one of the nice things that Hazelcast exposes is that the Hazelcast instance is the same between a client, basically a non-data node, and a full node which has data. So it gives you that flexibility where you can build a cluster where maybe some of your clients are no data nodes, and some of your clients are full data nodes that are actually doing replication. HazelcastMQ doesn't really know the difference. It just talks to whatever Hazelcast instance you give it, and so it doesn't care whether it's a full data node or not. So again, that gives you some flexibility as far as where your data is stored and how your clients are connecting. Then we create our Hazelcast MQ instance. This is exactly the same as what we did in the core demo. And then here we create our stomp server. And so here we're using the Hazelcast MQ stomp configuration. We're setting which message queue instance to use, what port to listen on, and then again, similar API, we create a new Hazelcast MQ stomp instance. And that becomes our stomp server. So at this point, the server is now up and running. So from there, we're going to use the stomp client that's part of the Yeti package, and we're going to go ahead and connect to that server on port 9001. Send our connect frame, send a stomp subscribe frame. Again, we use the same syntax for the destination, so we're subscribing to this topic, presentation.demo, and then we're going to put a frame listener. So again, it's event driven, so that as the frames come in, we're just going to print out that we got the message, and then we'll send another hello world, this time from the stomp application. So you can see the code's very similar. It's similar pattern: create Hazelcast instance, create an MQ instance, and then kind of create whatever integration layer you need. In this case, we're using stomp. So we'll go ahead and run this. All right, so again, you see the application is running, and then it got a message from itself saying hello world. And now if we flip back over to the core app, we'll also see that it got the message, because remember, we're sending to a topic, so it's broadcasting to everyone. And so in this case, we basically now we have integrated a client that's connecting via stomp using the stomp client, and a client that's actually fully written in Java, that's using the core interface directly. So you can imagine, instead of this stomp client, being in Java, if this was in, Python or C or C++ or .NET, whatever you want, you can go ahead and integrate the two, and it'll broadcast that message to anybody listening, no matter what integration method they're using. All right, so we'll leave those two running, and we'll come back to them in a minute. So next up is the JMS Provider. So like I said, HazelcastMQ itself exposes a JMS2-like API, although it's not fully JMS2 compliant. But originally, when I first started this, I needed to integrate into some existing solutions that were already using ActiveMQ and JMS. And so the simplest way to get HazelcastMQ integrated was to be able to just drop in a new JMS provider. And so I wrote this integration to implement the JMS 1.1 APIs, but map all them to the internal consumer and producer concept of HazelcastMQ core. So it works with Camel's JMS component as well as with Spring's JMS template. So if you already have a solution that's built on JMS, depending on your level of feature use, because it's not a full provider, because there are some JMS features that don't work yet, and I'll talk about them later. But depending on your use, if you're using kind of basic message passing, request reply stuff, you may be able to just drop this in as a turnkey solution and get rid of your JMS broker and be able to just build on top of your Hazelcast investment. I'm not going to go through an example of this. It's very similar to the Stomp integration that we saw, except that it'll expose a connection factory and a connection and a session and all that good JMS stuff. So the next up is the Camel component. And if you're not familiar, Camel is a framework that provides enterprise integration patterns. So it gives you the idea of building routes and transforming messages, processing messages, routing them to different endpoints. So it's a really great way, if you haven't used it yet, to kind of build a simple, service bus type architecture. where you can, in your Java application, you can actually expose everything as just a normal Java interface, and then under the hood, you can have that, do error handling, do routing, do message transformation, etc. So it really lets you, swap out and upgrade your message passing architecture without affecting any of the actual application architecture, which is a really cool framework. So after I did the switch, like I was talking about with swapping out ActiveMQ JMS for HazelcastMQ JMS, I was still using Camel's JMS component, which while it works pretty well, it can be pretty complex to configure. And under the hood, it's actually using a lot of Spring components to do that mapping. And so I thought, well, why don't we just integrate HazelcastMQ as a top-level Apache Camel component so that we don't need to use that JMS translation anymore out of Camel and then into HazelcastMQ. So I implemented this to map the Camel concepts of exchanges and messages to HazelcastMQ. And so it lets you use all the enterprise integration patterns within Camel and use HazelcastMQ as an endpoint just like any other endpoint. So it supports out only, in out, and in only messages, and in Camel in out essentially means request reply. And so that it really makes request reply super simple in the application, which means it's pretty easy to do RPC style messaging with Camel and HazelcastMQ, because Camel can expose a Java interface as a gateway to your message system. And so essentially you can pass parameters to your interface, and then you can get a return value from your method call in the interface. And underneath, what's actually happening is your message might be getting transformed, sent out across the cluster. Somebody answers it, sends back a value. From the Java code, it looks like just another method call. So kind of get you what EJB has always promised, but relatively easy and incredibly flexible because you're sitting on top of your Hazelcast cluster. So let's look at a quick example of that. And again, it's going to look very similar, which I think is a good thing. So again, we create a client. We're not running a full data node here, but you could start a data node here and have it just join the cluster rather than being a client to the node we're already running. But to keep it simple, we'll just use a client. Then we create our HazelcastMQ instance again, exact same code from before, and then we create our integration component. So in this case, it's going to be a Camel component rather than the Stomp server that we created last time. So again, you create the configuration, and then you create your the component, and you set the configuration on it. The rest of this is basically just Camel specific, where we're creating our Camel context, we're adding or registering our HazelcastMQ component, and then we're building our Camel routes. These are extremely simple routes. Normally you'd have a whole bunch of transformations or error handling and logging and things like that. But basically we're building two routes here, one that's reading in from this topic and just writing it to standard out, and then one that's reading from a Camel component called direct, which is essentially just an exchange handoff, and then it's sending it out to the topic. So you can see that we registered HazelcastMQ here, and so we just use that as the prefix for our endpoint. All right, so then down here, in this case, I'm using Camel's producer template, but like I said, if you were doing this for a full application, you probably want to use Camel support for proxying a message gateway so that you can use a real Java interface rather than having to use their producer-specific class. So we create our producer template, and then we're just going to send a message to this direct demo endpoint, and again, it's that hello world message, and then we shut down our producer. So this message is going to go to this endpoint, and then Camel is going to route it from that endpoint to Hazelcast. And then once it ends up on the topic, Hazelcast is going to broadcast it to all the topic listeners, so it's going to come back in this endpoint, and then we're going to print it out to standard out. So we'll go ahead and run this. Okay, again, same basic output. The application's running, and then we got our hello world message. This is getting printed by this stream output right here. And again, so if we flip back over and we look at the core app, we should see that here's our Stomp when Stomp joined, and then here's when Camel joined. So the topic got broadcast out to everyone. And again, if we flip over to Stomp, we see that it also got broadcast there. So basically now we have 3 different integrations running. We've got our core application that's using HazelcastMQ directly. the Stomp application that's connecting as a Stomp client and sending and receiving broadcast topic messages, and now we have Camel that's sending and receiving messages via Camel. And then in theory you could also add JMS, but I don't have a demo for that. But you can imagine it's very similar, and so any JMS client like Spring's JMS template would be able to send and receive messages as well. All right, so let's flip back to the slides. So what are some of the benefits of introducing HazelcastMQ into your application? Well, the most obvious is that it's built on top of Hazelcast, which solves a huge number of problems for you, like clustering, scaling, failover, etc. Hazelcast, like I said, has that integrated as a core concept, so it really works extremely well, and it's extremely easy, even without any configuration at all. As you spin up nodes, they're just going to join the cluster and start passing messaging around. You don't need to use any separate broker or separate machines. So you can use an embedded data client. You can use the Hazelcast client, or sorry, an embedded data node or a Hazelcast client. If you want, you can have the Hazelcast node running on a separate machine. It really doesn't matter. It has a lot of flexible ways to deploy it. So if you want just simple messaging inside of an application or between two applications, you could just do it by running a Hazelcast node inside the application and let it cluster between them. So it essentially abstracts away all of the network communication, so you don't need to worry about it. The HazelcastMQ provides a solid messaging-oriented API, so you don't have to reinvent the wheel. When you're working with Hazelcast Q and Topic, they work pretty well at the data structure level. But as soon as you want to get into message expiration or retries or routing or anything like that, you need to start introducing some messaging concepts. So you need to kind of get that out of the box with HazelcastMQ. It provides a standard language for cross application or cross language communication. So for example, if you wanted to use the Stomp interface, you can have Python clients and C clients, etc. And then it also integrates with JMS and Camel, so it lets you tie in any of your existing solutions on top of Hazelcast. I'm not going to go into any kind of a full discussion of messaging versus web services, but in general, there are a number of benefits that you get with using a message passing architecture and a service bus over direct web service calls. Using microservices and REST is all the rage right now, but it introduces a lot of problems you have to solve. One of the simplest is just node discovery. Trying to figure out what backends are available when one goes down, and so you start turning to DNS solutions or building some kind of registry or dynamic discovery. So a messaging solution can hide a lot of that. As long as someone's sitting on the message bus, or in this case, as long as you're sitting on a Hazelcast node, you can receive messages. Things get queued if a node goes up and down. You have options of rerouting things and stuff like that. Things that can be kind of hard when you're doing direct point-to-point calls, using SOAP or REST. So what are some of the limitations? And there are a number of them. The biggest being that HazelcastMQ right now does not provide any kind of fully reliable messaging. There's no ACKs or NACKs implemented, so essentially you should consider it working as basically auto ACK if you're familiar with the JMS world. So essentially, as soon as a consumer takes a message, it's assumed that they've processed it successfully. So if that consumer drops it or the consumer dies, the message does not get requeued. So that could be a deal breaker for some of your use cases. But I find that anytime you try to build a solution, assuming that the message broker is going to handle all those problems for you, it usually doesn't work out anyway. So if you're building with the idea of not reliable messaging from the beginning, then this isn't really a big deal. You have to just handle replaying things yourself or being eventually consistent. There's very limited in-flight message management right now. For example, flow control, dead letter routing, etc. Hazelcast does provide a JMX interface and their management center, so you do have some visibility into the Hazelcast nodes themselves. But you really don't have any control over flow control. For example, if you have fast producers and slow consumers, things are just going to queue up inside of Hazelcast. The good news is that Hazelcast scales very well, so if you find you have situations like that, you can easily just spin up another node and let it distribute the queue across all the nodes. So essentially, it'll scale as to as much memory as you have, but you can't slow down producers if things aren't getting consumed. And like any messaging system, it does carry some some baggage. I was just talking about the benefits of messaging over web services. Well, you also get some downsides with messaging over web services. For example, queue management, error handling, message tracking, etc. With point-to-point web services, it's pretty easy that if the other end's not there and you try to make a request, you figure it out pretty quickly and things fail. With messaging, you could send that request and it just disappears into the message bus someplace, and you have to try to figure out, well, did some node pull it off? Did the client disappear? What happened? So there are pros and cons that you need to consider when looking at any kind of messaging system. All right, so what you want to do with HazelcastMQ and Hazelcast. So in my opinion, microservices are a great opportunity for this type of framework, mostly because you'll probably be doing things like RPC style messaging, or you'll be doing batch processing where you're just kind of sending things out and waiting for someone to process it and give you an answer, and if they don't, you'll just send it again. So those kind of services really work well because you don't have to worry about reliable messaging quite as much, because you'll figure it out. If you don't get a reply in X amount of time, then you know that the request either wasn't received or the client died, and you can handle that yourself. Another interesting use case that's kind of really growing like crazy right now is stomp over WebSockets. Spring has pretty good support for this, and Hazelcast HazelcastMQ with the stomp component can kind of drop right in there. And so what that means is you can go all the way from the client's browser through WebSockets into HazelcastMQ's stomp server, and then basically broadcast that message on your or do point-to-point on your Hazelcast cluster. So it means you can have back-end services sitting on the cluster that are processing requests coming in from a front end directly from the client. So essentially you now have end-to-end communication all over just a Hazelcast cluster, which is a pretty exciting offers a lot of pretty exciting opportunities and use cases, I think. So another one is if you're doing any kind of send and forget broadcasting, I think that works really well. So for example, the old use case is a stock ticker type thing where you might have some back-end system that's just constantly broadcasting messages or events or status information, and you just want some front end to sit there and kind of listen to it and maybe display data. In that case, again, reliable messaging isn't important. It's more about throughput and speed. And so with an in-memory data grid like Hazelcast, essentially your data goes from one end to the other instantaneously. There's no persistence or queuing. And then again, batch processing. If you have a system that's eventually consistent, if a job fails, in one batch job, it'll get picked up in the next one. And another great place to use something like Hazelcast MQ. So where you should probably avoid it, again, financial processing or really anything where you have rules that say a message can never get lost, or a message can never not be handled. So if you need something that can provide 100% reliable messaging, this probably isn't it, at least right now, because of the lack of consumer transactions and ACKs and NACKs. It's on the roadmap. We'll see in a minute to add that, but for now, if you need 100% reliable messaging, it's probably not the answer. That being said, I would say that probably most of the message queues out there are probably not the answer. You probably want to solve it a different way. Hazelcast itself is kind of designed for fast communication on LAN. At least that's my personal experience. So as soon as you start to get into WAN clustering, I've seen things kind of get some weird situations where whenever it tries to synchronize the cluster, you end up waiting for your slowest WAN connection. So Hazelcast does have WAN replication, which works really well for a cache, but it doesn't work so well with a message queue because you could end up with duplicate messages if it replicates them, or if there's a lag in replication. So again, it works well with within a LAN or within a cluster, but probably not over a large network. And again, we've already talked about the no flow control. So, if you have irregular message production, we might have producers that, generate millions of messages, and then they, over the next 24 hours, the consumers slowly consume them. That could be problematic if you need, flow control on the producers. There are other options, for example, you can, like I said, you can scale out your Hazelcast cluster, or you can look at some of the new features coming in Hazelcast, like off-heap storage, so you can actually, just dedicate a huge amount of memory outside of the JVM for these situations. So depending on your use case, this may or may not be a reason to avoid it. All right. So then some of the future things that I have in mind, but I'm always welcome to feedback as to what direction people are interested in. So Spring integration is a big one for me, mostly because I've got a couple projects that are still using ActiveMQ because of the fact that they need transactional sends that essentially we only deliver messages if we can for example update some rows in a database. And so by tying into Spring's transaction management, I can link together HazelcastMQ producer send requests with overall Spring transactions like JDBC commits. So that's something I'm working on right now, and I'm hoping probably in a week or so to have at least a first cut at that. Like I said, ACNAC consumer transactions are pretty high on the list. I don't know how realistic it is, but it's definitely something I'm going to start exploring, just because it moves you one step closer to more reliable messaging and more ability to recover from errors. A JMS2 provider, if people are interested, I can do that. It should be relatively easy, just because Hazelcast core or HazelcastMQ core exposes JMS2 like API, so it should be fairly easy to implement the JMS interfaces on top of that. I haven't seen a lot of support libraries move to that very quickly, so it's not a super high priority. I am interested in exploring some of what's coming out with Hazelcast 3.3, such as the custom data structures that you can build on top of the core replication and networking, and looking at if that would work well for implementing selector support, or just faster, more specialized data structures for messaging aside from just the current queue and topic. And then like any good programmer, I always want to go back and refactor what I've already done. So I am interested in looking at kind of improving the internal thread model. Right now, the thread model is based on some of the JMS2 specifications as far as how you can use it for multiple threads and what's thread safe and what's not. And so I'll probably maintain that just so it's compatible with JMS2. But internally, I think I may be able to simplify it down a little bit. You're looking more to reactor pattern internally, but making sure that I stay consistent with the JMS specification, so that in the future JMS2 support's pretty easy to add. All right, so that's all I have to cover. I thank you all for coming, and I think at this point we'll jump into questions if anybody has questions. And like I said, there's a lot more examples in GitHub. The link is down here if you're interested. And thanks a lot. All right, so let me see what questions I've got here. So one of the questions, the advantages, limitations of HazelcastMQ versus ActiveMQ. So I tried to cover a few of those. I mean, ActiveMQ, has a gazillion features. HazelcastMQ has a very small subset of them. But the trade-off is that, in my opinion, ActiveMQ, it can be incredibly difficult to configure correctly. So even though you have all those features, I'm guessing that most people are not using them, or once you get them working, you're kind of afraid to ever touch it again. Especially when you start layering, Spring and then Camel on top of that, just because you're so abstracted away, and the JMS1 APIs have so many rules as far as thread safety and session reuse and connection connection reuse. It can become pretty tricky. So HazelcastMQ has a tiny fraction of those features, but as I just showed, you can get basic messaging embedded up and running in maybe 10 lines of code. So it's that trade-off of configurability versus simplicity. And then obviously, if you're already using Hazelcast for its caching and data grid features, it's kind of a no-brainer that you could do messaging over it as well and eliminate the entire message broker from your stack. Another message, does it scale if you add servers? Yeah, I mean, all I can say to that is it will scale as much as Hazelcast scales. So, like I said, it's a thin layer on top of Hazelcast Q and Topic. So, if Hazelcast can scale out to a infinitely large queue, then HazelcastMQ will as well. Am I using it in production? We're using it in production for a number of internal apps, mostly, like I said, for our soft real-time applications. I'm not currently using it for our main content management system, which probably has a different profile where it has higher load but less real-time requirements, only because I don't have the transaction support yet. So that's probably number one on my priority list is to get Spring transaction support, and then I'm going to be looking at transitioning that to using HazelcastMQ. Performance testing, I have not done any other than what's already publicly available for the Hazelcast itself. Almost everything delegates directly to a Hazelcast queue or topic, so I would expect it to scale, pretty close to whatever the Hazelcast metrics are. Some performance testing of my own. All right, well, that's all I have. Oh, another question. Like I said, from a performance point of view, sorry, the question is, what are the expected performance characteristics? I would expect it to be the same as Hazelcast itself. There's very little overhead added. That essentially it relies a lot on the event messages when a queue or topic is modified in Hazelcast, and then it directly passes messages straight into a Hazelcast queue or topic. So it should have similar performance characteristics to Hazelcast itself. But I have not officially verified that. All right, that's all I have. So I'll hand it back over to Andrea.
Thanks so much, Mike. And thanks again to everyone for joining. We'll be putting the recorded webinar on the website with Mike's slides and with code samples.